In this video, I'm going to be giving an introduction to absorption mode Fourier transform mass spectrometry. Sometimes absorption mode is also known as enhanced Fourier transform, or EFT, or AFT, or AMP, but underneath all of these acronyms is the same concept of absorption mode. And unlike the conventional method of viewing FTMS data, called the magnitude mode, with absorption mode it helps to understand a bit about what it is in order to help you get the benefits from it that you will be expecting. So I hope this video helps you understand what absorption mode is and how you can get the best out of it. Absorption mode and magnitude mode are simply two different ways of processing and viewing exactly the same FTMS data. But if you can view your spectrum in the absorption mode, you will be able to get more and better information out of it. Now the problem is that getting at the absorption mode comes with a few more complications than are needed to get at the magnitude mode spectrum. So before diving into those complications, let's look again at the benefits that processing your data in absorption mode will bring. The first benefit is improved resolution. In the absorption mode, you will tend to see your peak resolution approximately double, and this means you'll easily be able to find extra peaks in the absorption mode that you would never have been able to detect in the magnitude mode, especially in complex spectra. We can see this benefit here. This spectrum shows a small part of the data from a top-down fragmentation experiment recorded on a modified Orbitrap instrument. The magnitude mode spectrum is shown in black, while the absorption mode spectrum is shown in red. If you focus in on these regions, you can see the extra peaks that are now fully resolved in the absorption mode that would have been impossible to detect in the magnitude mode. Now this is important because missing peaks in your mass spectrum means that you're missing information about some or many of the components in your sample, and in some cases this can dramatically change your interpretation or the confidence you can place in your conclusions. Now in this region we can see a few extra peaks, but let's look at another region in exactly the same spectrum. Here we can really see the benefit that absorption mode can bring to your data processing. Just imagine how many more peaks can be seen across an entire spectrum. Okay, so improved resolution is the first benefit. The next benefit you'll see in absorption mode is the improved signal-to-noise ratio. This benefit comes from the underlying mass that is used to produce the absorption mode spectrum, and in practice this means you will see a basic improvement in the signal-to-noise of the square root of 2. A 1.4-fold improvement may not sound like much, but as mass spectroscopists we all know how often we're searching for important peaks down near the noise threshold, and so this 1.4-fold improvement can make all the difference between confidently locating a post-translational modification or missing it completely. There is an added benefit that in absorption mode you can also use more advanced apodization functions, and these can result in even larger increases in the signal-to-noise ratio for spectra with rapidly damping transients. But I'll be covering apodization in another video, so we won't worry about that just now. The final benefit is improved mass accuracy. Now this benefit comes from the combination of both of the previous two. Firstly, the peaks are more narrow, and so this obviously means you can define the centroid more accurately, but with the improved signal-to-noise ratio the noise now also has a reduced impact on the error of the peak position, and these two things combined means you can be much more precise about where the peak is. So what is the take-home message? Well, overall, the result of the three improvements of improved resolution, improved signal-to-noise ratio, and improved mass accuracy means that if you process your data in the absorption mode, you'll be able to detect more peaks in your spectra and you'll be able to assign them with more confidence. And so this is why, if it's possible, all FTMS data should really be processed in the absorption mode instead of the magnitude mode. So here we can see an absorption mode spectrum with what looks like two overlapping isotopic distributions that would not have been resolved in the magnitude mode. The problem is that this is not what this spectrum actually shows. So we'll come back to this later and hopefully you'll see what's gone wrong here. There are two major classes of FTMS instrument: the ion cyclotron resonance mass spectrometers and of course the Orbitraps. I'll look at the ICRs first and then I'll come back to the Orbitraps later. Here is an ICR instrument. This is actually the one at the University of Warwick in the UK. The big cylinder in the middle is the superconducting magnet. In the middle of the magnet is an ultra-high vacuum chamber, and that houses the ICR cell. And this part on the right is known as the cart. It actually provides a lot of the capabilities of the ICR, but for the purposes of this absorption mode introduction, its main job is to transfer the ions from atmospheric pressure into the cell. Underneath the cart you can see these breathing holes. These are where the pixies live. The pixies are essential to the running of the ICR, but they can be troublesome if not treated well. I find that pushing a banana through this grid once a week or so tends to solve most problems. But if you still have issues, then whispering compliments through the other grid can also be effective, although you might have to try a few different ones before you find the one that works. Here's a schematic of the instrument design inside the cart. Ions are created in the ion source, and then travel down through various ion funnels, quadrupoles and multipoles until they reach the cell in the ultra-high vacuum region. The cell is cylindrical in this case, and is about the same size as a baked bean can. The outside of the cylinder is split into 4 plates, but we'll cover them later. The important thing to notice now is the cylindrical axis is parallel to the magnetic field. In mass spectrometry, we're always measuring ions and not uncharged particles. Because these ions are charged and moving in a magnetic field, they feel a force that drives them into circular orbits, much like the force that causes electric motors to run. The frequency that ions oscillate with is called their cyclotron frequency, and is usually given the symbol little omega c. In fact, ion frequencies are often symbolized with little omega in equations. The cyclotron frequency of an ion is a function of its mass-to-charge ratio, meaning ions with different mass-to-charge ratios will oscillate at different frequencies. So if we can detect those frequencies, we can measure the masses of the ions, and this is the basis of ICR mass spectrometry. So how do you measure the ion frequencies in an ICR cell? So imagine this is a positive ion. When it's on this side of the cell, it will be attracting electrons into the surface of this plate. Then, when it's oscillated round to here, it will now be attracting electrons into the surface of this plate. By connecting those 2 plates up in a circuit, we can record the current generated by the electrons that are moved from one plate to the other by the motion of the ions. The charge attracted into the surface of the plates is known as the image charge, and the alternating current generated as the image charge moves around the cell is known as the ion transient current. The problem is, if we tried to record the ion transient just now, we'd get almost no signal to detect, and this is for 2 reasons. Firstly, when the ions are injected into the ICR cell, the radius of their oscillation is extremely small, less than a millimeter, so they're a very long way away from the plates and the image charge effect is very small. Secondly, for every ion that's on one side of the cell, there's another ion exactly counterbalancing it on the other side of the cell, and the net effect is that the image charges cancel out, and so you see no signal at all. So in order to be able to detect a signal in an ICR cell, we need to do 2 things. Firstly, we need to increase the ion cyclotron radius, so the ions are closer to the plates, and secondly, we need to introduce what's known as coherent motion, so that all the ions of a given mass to charge move around as a single packet, rather than having the ions randomly distributed around the cell. Luckily, we can induce both of those changes by applying an alternating potential to the other 2 plates in the cell. When the frequency of the alternating potential is the same as the cyclotron frequency of a given ion, then all the ions with that frequency will start to move together as a coherent packet, and the radius of the packet oscillation will increase. In mass spectrometry, we usually have a range of different ion masses in the cell, and therefore a range of different ion frequencies. In order to excite all of the ions, we can't simply apply a single excitation frequency, but instead we apply an excitation frequency sweep across all the range of frequencies we might expect to see in the cell. And now that we've induced large radius coherent motion of all the ions in the cell, we can turn the excitation function off, turn the oscilloscope back on the other plates, and record a much bigger ion transient signal. Of course, what we're really interested in is the component ion frequencies whose signals have summed up to give us the complete transient, and we access those frequencies by Fourier transforming the signal. If you're not comfortable with what the Fourier transform is actually doing, then I strongly recommend watching the YouTube visual introduction to the Fourier transform created by 3 Blue 1 Brown. I've provided a link here, but you can also find it by searching for 3 Blue 1 Brown Fourier on YouTube. It truly is an amazing graphic explanation to what the Fourier transform is, and I didn't really understand it until I watched that video. And it will provide excellent background material for helping to understand the remainder of this video. So I recommend pausing here, watching the 3 blue 1 brown introduction to the Fourier transform, and then carrying on from here again. Hopefully you recognise this view from the 3 blue 1 brown video. Up here you can see the waveforms. In this case the green waveform is the sum of 2 pure sine waves, shown in red and white. These two have frequencies of 2 and 3 Hz respectively. But it's the green waveform that contains both of those frequencies that is being Fourier transformed below. Down here is the winding graph, where we're winding the waveform around the origin at ever-increasing frequencies. The red spot is the centre of mass, basically the Fourier transform at each point. Over here is the Fourier transform result as it's calculated. This is plotted by following the position of the red dot for every frequency. Ignore the fact that there are two different plots here, we'll come back to them in a moment. Let's concentrate on the winding graph just now. Remember, this is where the waveform that is being analysed is being wound around the origin of the plot at different frequencies. At each frequency we calculate the average centre of mass, and that's shown by the red dot. Actually, I've exaggerated its position by doubling its displacement in both directions, but that's just to make it easier to see. For every frequency, the red dot gives the value of the Fourier transform at that point. Notice that the axes of this plot are labelled as real and imaginary, so that means we can describe the position of the centre of mass according to its coordinates in the real and imaginary directions. But there's another way you can also describe the position of a point in 2 dimensions, and that's using polar coordinates. In this case these are the magnitude and phase angle. So the position of the red spot can be described by either its real and imaginary Cartesian coordinates, or by its magnitudes and phase angle in polar terms, and you can switch from one form to the other by simply using Pythagoras or trigonometry. For me, when thinking about what the position of the red dot means in reality, the polar view is much more intuitive. Remember, we're talking about sinusoidal signals created as the ions rotate round inside the ICR cell, so thinking about their real and imaginary parts doesn't really mean anything, but thinking about the position of the red dot in polar view makes total sense. The magnitude is the measure of the amplitude of the signal, while the phase angle tells us the starting angle of the signal, basically how far the signal is shifted along the time axis, or more accurately how far around the cell the ion packet was when we started recording the transient. So let's go back to this view. What were the 2 different lines I was drawing in the Fourier transform graph? If we plot the real coordinate of the red spot for every frequency, we get the white spectrum. And if instead of the real coordinate we plot the magnitude of the red dot, we get the red spectrum. The red spectrum, where we've plotted the magnitude of the red dot, is known as the magnitude mode spectrum. Historically, this has been the normal way of viewing FTMS mass spectra. The white spectrum, where we've plotted the real coordinate of the red dot, is known as the absorption mode spectrum. And you can see the improved resolving power in the absorption mode spectrum even in this simple model. Okay, so we've looked at the basis of the 2 different modes of FTMS spectra. There's the magnitude mode, that's traditionally been the normal view, and the absorption mode, that is this more advanced view that gives you better spectra. To get the magnitude mode view, we think about the output of the Fourier transform in polar terms, and plot the magnitude of the signal at every frequency. Whereas to get the absorption mode, we think about the output of the Fourier transform in Cartesian terms, and plot the real coordinate of the signal at every frequency. So really getting either the magnitude or absorption mode sounds pretty easy, right? If we try this simple approach, we do indeed get the magnitude mode spectrum we expect. But unfortunately the absorption mode spectrum looks like this. Something's obviously not right. Some of the peaks are positive, but some are completely negative. And many are somewhere in between. So what's gone wrong to cause this distortion of the absorption mode spectrum? and how can we fix it? To understand what's gone wrong, let's go back to the winding graph idea. Imagine we've recorded a spectrum in an FTIC-RMS, and let's just consider one of the peaks in that spectrum for a single ion, and regenerate the winding graph for that ion's frequency. Remember, the centre of mass of the winding graph, for that frequency, was shown by the red dot, and this gave us the Fourier transform result at that frequency. Thinking about the position of that red dot in polar terms, the magnitude of the point gives us the amplitude of the ion signal, and the phase angle tells us the starting angle of the ion relative to the cell. If we want to get the corresponding absorption mode peak height, we'll have to take the real coordinate of the red point. If the phase angle for the signal for an ion is 0, then the red dot plots exactly on the real axis. And this means that at the peak top, the magnitude and the real coordinate have the same value. So the peak in the absorption mode will be the same height as the peak in the magnitude mode. If the signal for that ion was 90 degrees out of phase, however, then the red dot would plot on the imaginary axis. The magnitude hasn't changed, so the magnitude peak looks the same, but the real coordinate of this point is 0, so in the absorption mode spectrum, instead of a peak, we have a 0 crossing. If the signal for that ion was 180 degrees out of phase, then the red dot would have rotated back around onto the real axis again, only this time on the negative side. Still, the magnitude hasn't changed, so the magnitude peak still looks the same, but the real coordinate of this point is now negative, so in the absorption mode spectrum we would have a negative peak. Obviously, the phase angle of the ion signal is having a major effect on the absorption mode peak symmetry. If I sweep this phase angle through complete rotations, you can see how the absorption mode peak shape changes. So remember the distorted absorption mode spectrum, where some peaks were positive, but some were negative and many were somewhere in between. What this is telling us is that the signals from all the ions have different phase angles. So why do the ions have different phase angles? We need to know this because then we can correct for the effect and show the real absorption mode spectrum. In ICR, these phase shifts are the result of how the ions have been excited before the detection of their motion began. Remember, to begin with, the ions have a very small cyclotron radius and are moving randomly. Then, in order to increase the oscillation radius and to cause all the ions to move around coherently with other ions of the same frequency, we applied an excitation signal across the cell, and then swept the frequency of that signal across the frequency range of the ion masses we were interested in. Ions are only excited into coherent motion when the excitation frequency is the same as their cyclotron frequency. Then we also have to leave a short delay between the generation of that excitation signal and when we turn the detection electronics on to collect the ion transient. This means that ions are excited at different times, and are then left to rotate around the cell at their own cyclotron frequencies before detection starts. We can see that effect here. In this ICR cell, I have 3 ions of different masses and hence different frequencies. When I start the excitation sweep, first one, then the next, and finally the third ion is excited. By the time detection starts, each ion has rotated round to a different position in the cell, and these positions will dictate the phase angle that each corresponding signal will start with. So if we want to be able to show the undistorted absorption mode spectrum, we need to be able to calculate or predict these phase angles, so we can correct for them and make it appear, mathematically at least, as though all the ions started from the same time and the same place with a phase angle of 0. Up to this point, I've only explained the source of phase shifts in ion cyclotron resonance mass spectrometry. So now let's look at the same effect in the Orbitrap. Here's a schematic of an Orbitrap Q-exactive instrument, but the important features are broadly consistent for all commercial versions. Prior to entering the Orbitrap, ions to be analysed are collected in the C-trap. Next, these ions are accelerated out of the C-trap towards the Orbitrap. This process has a similar effect to accelerating ions out of a time-of-flight source, so that the lightest, or more accurately the lowest mass-to-charge ratio ions, travel the fastest, and the heavier ions travel more slowly. This means that the lightest ions reach the orbitrap first and start oscillating along the length of the central spindle, and the heavier ones join them later. By the time the ion transient recording starts, ions of different masses have been oscillating inside the orbitrap for different lengths of time, and so just like the ICR, there's a systematic shift in the phase angle for ions across the mass range in an orbitrap spectrum. In order to produce a useful absorption mode spectrum from either an FTICR or orbitrap, we need to be able to generate a phase correction function that we can use to correct for the systematically varying phase angle that we detect in the different ion signals. As it happens, the phase correction function is broadly quadratic for both ICR and orbitraps. However, if we just had to solve a simple curve like this, it would be very easy, but sadly there are a few complications. The first of these complications is that phase is an angle. So in terms of degrees, you can have angles from 0 to 359 degrees and then you wrap back round to 0 again. So instead of a nice continuous curve, we end up with this sawtooth discontinuous function. Every time the phase angle jumps from the end of one circuit to the beginning of the other, that's known as a phase wrap. In this simple example I'm showing in the graphic, there's only 8 phase wraps, but in a real ICR spectrum there could be hundreds of thousands of phase wraps across the spectrum. Even despite this, if we had a nice well-sampled curve like this, then we could still solve for this function. But in real ICR or orbitrap data, we only get a point on the function where we have a peak in the spectrum. And these peaks are usually fairly widely spaced, at least in terms of the rate of phase wrapping, because you can get an entire phase wrap across the width of a single spectral peak, and there may actually be tens, hundreds, or even thousands of phase wraps between adjacent peaks in a spectrum. So instead of our nicely well-sampled sawtooth function that's easy to solve, what we actually end up with is a very sparsely sampled function. Because this function is sparsely sampled, you can't solve it algebraically, so we need to find other solutions instead, and here there are a few options. You can try to predict the function based on knowing how the ions were excited in the ICR cell, or how they were accelerated into the orbitrap. Or you can try to solve for the phase correction function using data within the spectrum itself. Both of these options work quite effectively, but there are two things to watch out for. Firstly, what you thought the instrument did to the ions in terms of ICR excitation or acceleration into the orbitrap may not be exactly what really happened. So perhaps the voltages or timings used weren't accurate enough for the predicted phase correction function to be applied successfully. Secondly, the ion population in the instrument actually generates its own fields, and these fields have an effect on the ion motion. So if the ion population changes from spectrum to spectrum, it can have an effect on the phase correction function. For both of these reasons, it can be very important to optimize the phase correction function for each spectrum. Here's an example of that effect. Here you can see an absorption mode spectrum that was phase corrected using a predicted function, and you can see in this case it hasn't worked properly. However, after optimization, here we can see a properly corrected spectrum. One great feature of the absorption mode are the negative side lobes on either side of the peaks in the spectrum. Now I know many people are not used to seeing these, but they do contain a lot of great information. Firstly, they are sometimes the easiest way to quickly recognize if the spectrum is well phase corrected. You should be looking to see if the side lobes are nice and symmetrical across your spectrum. If they are not, then that might indicate a phase correction problem. Secondly, if you have a well phase corrected spectrum and a small number of peaks within it are not well phase corrected, then you'll be able to see this because their side lobes will be unusually poorly symmetrical compared to the other peaks in the spectrum. This tells you something important about those ions. For some reason they haven't ended up with the right phase angle for the frequency they were detected at. So this could be because their frequency has been shifted, perhaps by space charge or peak coalescence. In that case, maybe you would not expect the mass accuracy of those peaks to be as high as for other peaks in the spectrum, and you can take this into account during assignment. Or maybe these poorly phased peaks are actually harmonics or some other signals contaminating your data, in which case any assignment for them must be wrong. So because these side lobes can give you such great insight into the quality of your spectrum, my advice is to make use of them if your data system allows you to see them. For presentation purposes, however, because seeing the side lobes doesn't really have any effect on the peak positions, and because many people are not commonly used to seeing negative side lobes in mass spectra, it can be useful to squash those side lobes down, or even delete them entirely. But do you remember this example from the beginning of the video? This is a case illustrating the perils of ignoring the information in the side lobes of an absorption mode spectrum. This spectrum looks like it shows two overlapping isotopic distributions with the same charge state. But looks can be deceptive, and this kind of thing can be dangerous. I mean, I look like the kind of hero you'd expect to play the lead in any number of Hollywood blockbusters. But in reality, I'm a slavering maniac who shouldn't be allowed anywhere near poultry farms after dark. Similarly, this spectrum harbours a dark secret. Often you can't do this, but if I superimpose the magnitude mode spectrum over the absorption mode spectrum, we can see the original peaks. So in this case, is the absorption mode simply able to resolve peaks when the magnitude mode could not? It's only if you view the full absorption mode spectrum then you can see what's happened. This region of the spectrum is actually so poorly phase corrected that these absorption mode peaks are almost exactly 180 degrees out of phase. And what we thought were peaks were really just the side lobes of the actual peaks. If we optimize the phase correction function properly, this is what the real peak distribution should look like. So now we come to the last thing I wanted to cover in this video, and that is the similarity between internal phase correction and internal mass recalibration. To optimize the phase correction function for a spectrum, we use the phase values for some peaks in the spectrum to fit to a theoretical curve, and this is very similar to the concept of internal mass recalibration. So when you're looking at your spectrum before trying to optimize the phase correction function, you need to check to see that you have sufficient high quality peaks across the spectrum, and that those peaks have a high enough signal to noise ratio and are separated from adjacent peaks. Essentially, you're looking for peaks with the same qualities that you'd be using to select those peaks to be used for internal mass recalibration. If your spectrum only consists of very low signal to noise peaks or has insufficient resolution such that all the major peaks are not well resolved, then you, or your software, may well have difficulty in successfully optimizing a high quality phase correction function. Okay, you've made it all the way to the end. Absorption mode is another way of viewing FTMS data that offers improved resolution, improved signal to noise, and improved mass accuracy, meaning you'll be able to see more peaks in your spectra and be able to assign them more confidently. We plot absorption mode spectra by plotting the real coordinate of every point in the Fourier transform of the original ion transient. However, we need to correct for the systematic variation of phase angle across the mass range, otherwise our absorption mode spectrum might contain distorted peaks. If you can, always view the full absorption mode spectrum. Don't be afraid of the negative side lobes, they can tell you important information about the quality of the spectrum and the quality of the phase correction. Always be wary of the situation where you had a single peak in the normal magnitude mode, but two much smaller peaks in the absorption mode. Is that evidence of a problem in the phase correction? And finally, in order to successfully phase correct an absorption mode spectrum, you will probably need there to be sufficient good quality peaks across the mass range to allow the phase correction to be optimized. Thanks for watching this introduction to absorption mode Fourier transform mass spectrometry. If you want any more help with absorption mode or any other mass spectrometry problem, then please get in touch through www.kilgourlab.com. And finally, remember, if you are feeding the pixies in your FTMS using bananas, please use organic bananas, as this will always give you the moral high ground when you have to explain it to your professor.